record on this computer. Yeah, so basically, as I was mentioning on the chat, I expect the grades for the second midterm to be posted sometime early next week, probably next Monday or Tuesday. But so far they seem to be going pretty well. Our exam, I already sent an announcement about the exam when it's taking place, the final. I mean, for the final, I decided it made sense to let you bring like a formula sheet. So, well, I'll tell you more about it on the announcement. But it says, well, I think it was there already, but it's essentially like piece of paper. You can write anything you want on both sides. And yeah, I won't like check what you write. So, but it is useful for the final to have the formula sheet because now in the remaining lectures, we will have like a couple of things that are difficult to memorize. So it's you can write those things out, and also you can write anything from the first two midterms on the formula sheet. So it will be up to you. But yeah, I'll give you more details about the final exam, like maybe in 1 week or so, after like I have like a better sense of all the topics that we'll end up covering. Um, if that sounds good. So for today, we have to talk about orthogonality. It is, okay, today is probably one of these lectures, which is a little bit heavy on the theory, more than I would like, but it is just something we need to do. And like next time, when we meet on Monday, I'll give you like examples and things like that so that you see how we're going to use it. But it is, yeah, today is kind of like one of those like lectures which is a little bit painful, but it won't like next week we'll get to more concrete things again. So but yeah, feel free to interrupt me at any time. I'm recording the lectures anyway, so I'll share with you the notes that I take on the iPad after we're done. So what do I mean by orthogonality? So for that, we have to go back to the dot product between vectors, which I had mentioned very briefly at the beginning of the course. But now we do need to use it a lot more. So if you remember how this dot product thing worked, you had a vector u and you had a vector v, okay? There's an angle between them, which I'm calling theta. And the dot product, u dot v, let's see. This is the name for, you may have seen this dot product multiple times in your physics classes. If you ever take multivariable calculus, it would also appear there. I think in statistics, like you also see it a little bit. It is like a very common operation between vectors. So if you remember like the definition of the dot product, what you do is multiply the length of the vectors times the cosine of the angle between them. Okay, so this is the key formula for the dot product. Okay, again, here when I put the vectors in absolute values, I don't know if I had mentioned that, but when you put like a vector in absolute values, like that just means refers to like the length of the vector or the magnitude of the vector. That's also another name for this symbol. So this is called the length or magnitude or norm. That's like, those are the three names that you typically give to this quantity of the vector. So far, so good. Now, there was this formula for the dot product, which again, I may have said very quickly at the beginning of the class, of the course, but we have used implicitly when we were doing matrix multiplications. So if you remember like the formula for the dot product, the idea was like if the vector has like n entries, so u1, u2, u3, up to un, and the second vector has another different entries, so v3 up to vn, then this dot product is essentially what you get by multiplying their corresponding entries and adding them together. So u dot v is u1 v1 plus u2 v2 plus u3 v3 up to un vn. Okay, so this is the other important formula for the dot product. Is that making sense? So for example, um, just to give you like something concrete, if u is like 1, -2, 3, 4, and v is like 2, 3, 4, 5, then u dot v, what would it be? It would be like the first two entries gives you 2, the second two entries, when you multiply then gives you -6, the third entries give you 12, the last entry gives you 20, right? So this is 32, 34, what is that, 28? So that's 28 in this case. Any questions up to this point? So far so good. Okay, so again, the of the stuff I have said, um, this is important. This formula for the dot product, this interpretation of the dot product in terms of the lengths of the vectors and the angle, and this one that is in terms of the entries. Okay, so let me copy this one again. In fact, copy, paste. So what are there are like two consequences of this formula which are useful to know. Okay, the first one is what do you think happens if you take the dot product of a vector with itself? What should the answer be if you look at this formula? U squared, yeah, because the angle of a vector with itself is just 0, right? The vector, like it just coincides. And so cosine of 0 is 1. So that gives you u squared. And when we say u squared, I mean like the length square of the vector. And another important consequence, so this is the first important fact that you should know. Here's the second important fact that you should know about the dot product, which these two are the ones that we will be using the most throughout the remaining part of the course. So the other important fact is like if you have u here, right, and you have v here, then what's the angle? Sorry, and let's assume that the angle between them is 90 degrees, right? So theta equals pi over 2 or 90 degrees. So what's the dot product in that case for u and v? It's just zero, right? So because cosine of 90 is zero. Um, so in fact, like the dot product is a way to detect when two vectors are perpendicular. So like that's like the only that's like one of the reasons why it's so useful. So u dot v equals zero precisely when the vectors um when the vectors u and v are perpendicular. Okay. So this is also called perpendicular vectors are also called orthogonal. So let me give you like this remark. So that's why I called today's lesson orthogonality. That's another way of saying I guess it sounds better than perpendicularity. So well, maybe that's why people decided to give a second name to this property. But I'm just saying that whenever you talk about two vectors being perpendicular, it's the same as saying that the vectors are orthogonal. Okay. Any questions up to this point? I'm not going to tell you why we care about this, um, unless there are any questions first. By the way, feel free to unmute yourself or just type it on the chat if you prefer. And you can also send me like one of these private messages on the chat as well. So whatever works best for you. Where do I have my vector? Give me a second to see. Oh, here they have. I have. Just in case I need them. So now I'm going to explain to you why do we care about these perpendicular vectors. So up to this point, when we had like vector spaces, right, we were interested in finding a basis for that vector space. But maybe you notice like from the examples up to that, you know, a given vector space can have multiple bases, right? Like having a basis is not like something unique. So different people can find different bases for the same vector space, and that's fine. So there's a lot of like freedom when it comes to finding bases. And so what we want to do is kind of like put more restrictions on what properties we want the basis to have. So it turns out that a very useful property for a basis to have is for the vectors in the basis of the basis to be orthonormal. So let me explain what I mean by that. So a basis V1, V2 up to Vn of a vector space is called orthonormal if two things happen. Each vector has a length 1. Each vector of the basis, I should just to make it more clear, of the vector has of the basis has length 1. So that means that the length of vi equals 1 for I equals 1 2, 3, up to n. Okay. And the more that's useful, but the one that's really crucial that makes this concept very important is that each any two vectors in this basis are mutually perpendicular. Okay. Any two vectors of this basis are perpendicular to one another. So what I mean by that is that say remember now saying that they're perpendicular means that their dot product is zero. That's like our mathematical way of saying to linear algebra way of saying that the vectors are perpendicular. So what I'm trying to say is that v1 dot vj equals 0 whenever I is different from j. Okay, so this is like a very important definition of throughout for the remaining part of the course. Okay, so that's again, it means I'll give you a second to copy this, but it means vectors are perpendicular in the basis and each vector has like length 1. That's also called univectors, if you're interested in that name. So sometimes when a vector has length 1, you just call it a unit vector. Okay. So I'm about to give you a couple of examples in a moment before telling you why this is useful. But so far so good. Any questions up to this point? Is that okay? Okay, so let me give you two examples of an orthonormal basis, and then I'll tell you in general why we want this property to work. So here's two examples. Imagine that the vector space is R2, okay? So if you remember in R2, you have these two basic vectors, which are called E1 and E2, which in the physics courses or like other courses are called I and J. So here's I or E1, and here's J or E2. So they mean the same thing. So first, remember that these two vectors form a basis of R2 because any arbitrary vector can be decomposed as a linear combination of these two. But the important thing for us right now is that this basis is an orthonormal basis of R2. Form an orthonormal basis of R2. That making sense because uh, you see, like their angle is 90 degrees. Hopefully that's clear here, right? Because they point along the x and y axis, which we always take as being perpendicular. And I mean, each one has length 1. So um, they just satisfy the two extra conditions for being an orthonormal basis. Is that okay? So far, so good. Any questions about this first example? Now, maybe I'll give you a second to think about it. But that my claim, or what I'm trying to say, is that this E1, E2 are not the only orthonormal bases of R2. There are other bases of R2 that are orthonormal. So, I mean, I don't know if anyone wants to try to think about what could be another possibility. Unless, yeah, let me give you like a minute to, or someone wants to think about, give a proposal, you can type it on the chat. If not, I'll just tell you what it is. Yes, I that works. It's true, but we can do even slight like that is not that basis you're giving is not too different from the one I wrote because you just multiply them by -1, which is fine. But there's a little but they kind of are almost like the same vectors because they're parallel, right? I want something where the vectors kind of like look a lot more different than E1 and E2. So it's that one works and it's a second orthonormal basis, but I'm looking for something slightly more like spicy. Ooh, excellent, excellent. So yeah, I like that. So that's like the idea. Well, imagine that these two vectors had the same length. Unfortunately, I purchased on Amazon vectors of different length. So what we can do is rotate them. So I'm going to rotate them. If you remember with these rotation matrices that we saw at the beginning of the course, and that will give me another basis. So let me make it more concrete. If I take like a rotation of 45 degrees, right? So when I rotate E1 45 degrees, I get this vector, which I'll call V1, which is 1 over root of 2, 1 over root of 2. And if I rotate E2, I get this other vector, which is minus 1 over root of 2, 1 over root of 2. So they actually come from cosine and sine because like sine of 45, is 1 over root of 2. So, and same for cosine. So that's actually where they're coming from. But if you wanted to figure out them from the formula of rotation matrix, in the rotation matrix, you plug in theta equals 5 degrees, and then you just multiply them by E1 and E2, and that's how you obtain these two. Okay. So this, again, they have length 1. And they're mutually perpendicular. How do you know they're mutually perpendicular if you didn't want to trust the picture? Well, when you do their dot product, right? When you do the dot product of this one with this one, that gives you -1/2. And the dot product of this entry with this entry gives you 1/2. So for the dot product, you have to add them. So you get -1/2 plus 1/2, and that gives you 0. Okay. So what I'm trying to say is that V1, V2 form a second orthonormal basis of R2. Is that making sense? So far, so good. And in fact, like again, for every angle of rotation, you could get like a different basis, which is orthonormal. So that's why these rotation matrices were like useful. They give you like quick examples of these things. Is that okay? Any questions about this? Okay, now let me explain why we care about these bases. So why do we want to find orthonormal bases? What's the point? Why do we want orthonormal bases? Just to make it more general, you'll see why you'll see that the formula works essentially the same way regardless of uh, of the number of the dimension of the vector space. But let's say that like the vector space was like R3, just so that I can still make pictures. So you should think about an orthonormal basis of R3. It's more, I mean, it's not all the examples come from this, but like the majority come from this. So you take the XYZ axis, each of them, and you kind of rotate them, you know. So maybe V1 looks like here, and V2 looks like this, and V3 looks like this. I don't know if you can kind of see that it is like if someone had taken the three axis and did like a rotation. Again, that's like many examples of like orthonormal bases just come from that idea. There are other things that could happen, like because you are allowed to reflect them. So you can look at the mirror image and other, there are a few, I mean, it's essentially like a rotation and a reflection, basically. But we won't get into those details of like what are all the possible orthonormal bases, but that's more or less how they can be found. So let's say you had like another orthonormal basis, okay? So if they're like, let me write it this, V1, V2, V3, they are like an orthonormal basis of R3. Well, so the idea is that if you choose like a random vector, right? If this point is if this is a random vector in space, then the fact that these three vectors are a basis means that this vector can be written as a linear combination. So V is like C1, C2, C3. Right. So any vector on R3 would be can be expressed as a linear combination of the vectors V1, V2, V3. Right. That's what it means to be a basis. Okay. So that's all good. And that is, I mean, that doesn't use at all the fact that they are orthonormal. That just uses the property of being a basis. But what happens is that if the basis happens to be orthonormal, then it is possible to give like a very simple expression for what these coefficients C1, C2, C3 are. Okay. So let me explain how this works. So imagine that I wanted to find C3, or let's say I want to find C1 just because it's easier here. So this is an equation between vectors, okay? And since this is an equation between vectors, what I'm going to do is take the dot product on each side of the equation with a specific vector. So I'm going to take the dot product of this equation with V1. Oops. Yeah, let me use a different color purple here just to emphasize that I'm choosing this equation. So I'm taking the dot product on both sides of the equation with V1. Okay. So what happens here? Well, the left-hand side, we don't know what that is. So let me just leave it like that. It is the same. I mean, we don't know what the vectors are, so I don't know how to compute this dot product. but the right-hand side can be worked out a little bit more in a way that's convenient. So, I mean, this may be more clear for those of you who have seen the dot product before, but what is a thing you can do to find out this dot product? When you do like, you have like a dot product of a sum of vectors dot another vector, what can you do? Yeah, so basically you can distribute. So what I'm trying to say is that you can do like C1, let me write it down. So is that clear? So what I did was distribute. So it gives you V1 with V1, V2 with V2 with V1, and V3 with V1. Is that making sense? And when I say and there's a dot product between these operations. Now the cool thing is that you can, because this is orthonormal basis, that's where we're about to use this information. Because this is orthonormal, I can actually tell you straight away what these two dot products should be, right? What are those two dot products? They're zero because being orthonormal means that the vectors are perpendiculars when they're different. So those two are like a 90-degree angle. So each one is zero because remember the dot product of perpendicular vectors is zero. So this is zero and this is zero because vectors are perpendicular. Cosine of 90 is zero, correct? Yes, that's like the, right, that's what gets used a lot of the times for these things. Yeah. Good. Is that making sense? And what's cool is that we can also say what this dot product of a vector with itself is. That's another that's the first property of orthonormal basis that I haven't used yet. So what can I say is this dot product? Equals the square of the magnitude, perfect. That's true in general, but for an orthonormal basis, we know that the magnitude has a specific value, right? It's one because it's one squared, right? Because it's a unit vector, but one squared is just one. Okay? So all of this is just to say that this gives you like a formula for the first coefficient of the linear combination in terms of a dot product. So the summary of our calculations, summarizing this, what this is saying is that C1, right? If you see like the only thing that survives this equation is C1. So that's saying that the dot product of V with V1 is C1. And that's something that we never had before, because before, like, if you wanted to express a vector as a linear combination, you would just need to solve a system of equations, of linear equations. Now you can just find like a dot product and then you're done. And so that's like the advantage. So let me write it like, let me write this in general so that you see like the key formula of like, this is like the key property of an orthonormal basis. That if V1 V2 up to Vn are an orthonormal basis, and V is an arbitrary vector, then V is V dot V1 times V1 plus V dot V2 times V2 plus V dot V3 times V3, blah, 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 up to V dot Vn times Vn. Okay, so this is like a formula that tells you how to express the vector as a linear combination. Is that making sense? So again, like the important thing is that it gives you the coefficients of the linear combination, which in general is not easy to find if you don't know that the basis is orthonormal. Is that making sense? Okay, now uh we'll use this next time. Now what I have to explain is how to produce an orthonormal basis, because for now we just have assumed that we were given one from heaven, but in practice you need to be able to construct an orthonormal basis. So the question is like, now how do you find an orthonormal basis? So okay, and for that we're going to do something which is called the Gram-Schmidt process, or algorithm that will produce for us an orthonormal basis. But before doing that, let's just focus first. Well, no, let's do it like, I'll do it this other way. Okay, so we're going to use something that's called the Gram-Schmidt algorithm. Those are, I guess, the people who came up with it, though sometimes the names of like the results don't correspond to the person who created them. Algorithm. GSA to just use an acronym. So what this method is going to give you is that you start with arbitrary basis, U1, U2, U3. So this is like an arbitrary basis. And the Gram-Schmidt process, GSA, will produce for you like an orthonormal basis. Okay, so like in Gram-Schmidt, like if you want like a picture, maybe like, you know, U1, U2, U3 looks like this, like assuming that like the basis, like the basis was of three vectors, so that I can draw some pictures. So maybe the vectors start like this, right? Like they are like a basis, but they're not perpendicular if you look at the picture, and they could also have like different lengths. And the process, like the algorithm, what it's supposed to do is kind of like straighten it out for you. It kind of like makes the vector, modifies like turn modifies the vectors a little bit to make them perpendicular. Okay, so it will, like, after the Gram-Schmidt method is done, you end up getting something that looks like more like what you would expect. Maybe something like this. Is that making sense? So like the method is kind of like the input is some random basis. The output is kind of like the basis, like the orthonormal basis associated to it. Kind of, kind of like that. Is that okay? So this is one of, as I mentioned at the beginning of the lecture, like for the final, I'll let you bring like a formula sheet, because there are just more things that are hard to memorize, and this on this part of the course. So this is one of those that I recommend definitely for you to write down on the formula sheet, because it is a bit messy. Um, so like what I'll do in like the remaining part of today is I give you like explain to you how this is supposed to work if the basis has like 3 vectors, because there I can do pictures. And then next time when we begin class Monday, I'll just give you like the full algorithm that works regardless of the number of vectors. But it's like a long computation. Like in practice, like I wouldn't ask you to find it for something bigger than 3, for a basis bigger than 3 vectors, just because it would take forever. It is a long process. So like you'll see why in a second once I start once I start explaining the algorithm. Okay, but yeah, for today I'll just for to illustrate everything, I'll do it with assuming that you have 3 vectors to work with, if that's okay. And then next time I'll explain it like in full generality. Okay, so I'm about to tell you how to make them perpendicular, basically. So the idea is that the process requires several steps. So in step one, step one like the idea of step one is just to pretend that you have one vector, one of the 3 vectors. I mean, I assume that you just labeled them. So there's a first vector, second vector, third vector. So step one just acts as if this were the only vector around. So we just take U1. Okay. So the idea is that you started with this vector. Oh, here it is. I have my vectors around. So let's say that you had this vector. I'm pretending that this is the only vector that exists on the basis, and I want to make it orthonormal basis. Assume that there was only one. Well, if there's only one, like we don't have to worry about the condition of this vector being perpendicular to other vectors, because now this is the only one around. So the only thing that we need for an orthonormal basis, if this were the only one around, would be to make it a unit vector, make it of length 1. Okay, so the first step is actually the easiest. It just starts with this arbitrary vector and makes it of size 1. Okay, so there's a trick that you can start with a random vector and turn it of a size 1, which is basically by rescaling it. So is that making sense? I don't know if this formula is kind of clear. So what I'm saying is that like the in the first step, what you just do is like divide a vector for by its length, because if you divide a vector by its length, it kind of that makes the length of the new vector equal to one. Is that kind of plausible? And now this is kind of like, think of these three vectors, U1, U3, U1, U2, U3 as kind of toys that had like a defect. So the algorithm is kind of like a machine that fixes it, right? So after we fix the first toy, we just throw the old copy away. So this old vector never stops existing for us. Like, so now the basis becomes D1 followed by U2, U3. Okay, so now we have a new basis. Is that okay? So because again, like the idea is kind of we're fixing the toy. So we have to, once we fix one, like we don't care about how it looked in the past. So now we're working with these three vectors. Okay, so you want like stop, like went away in the calculations. I mean, if you have written computer software, like this would look very familiar, because it's kind of like you are replacing like the variable with the new value or whatever. If you know what I mean. So that like the program will once you call for this this quantity will be using the value that we just found, or the updated version of this value. Okay. So now let's go to step 2. Any questions up to this point? So far, so good. This is where it gets a little bit more dicey, so we have to think about it some more. So in step two, now we keep track. Sorry, I should have used this with different colors. So now in step 2, we're using V1 and U2. Okay. So how do they look? Well, V1, we know that it is of size 1. So let me try to make something of size 1 here. And U2 maybe is bigger, so it looks like this. Okay. The thing is, like, their angle may not be they may not be perpendicular at the moment. Okay. So the end result of this algorithm, what we want to happen is that by the end of this process, like, we don't want to modify V1 again. This one should go. I mean, we don't want to be doing more work on the fixed toy. So this one should be fine, but we want to straighten out the U2 so that it looks like perpendicular to V1. Is that making sense? And we also rescale it so that it has length 1. So essentially, the second step is kind of like fixing U2 so that it looks perpendicular to V1. Okay. But the fix takes a little bit of ingenuity. So that's why now I have to tell you a little bit about vector projections. So let me like zoom in on this picture. And exaggerate a little bit here, what's going on. So there's this concept called like a vector projection. Let me see if I can choose a color which is stronger. So let me make it orange. Okay. So you have the sun. And if you imagine like the light, you can look at the shadow that this U2 vector makes along V1. Let me put this shadow here. Can everyone see it? So like they're like this light rays, blah, 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 blah. And so U2 forms like a shadow along the V1, which I'm not thinking of it being like some sort of floor. Okay, so this shadow vector is called the projection. Projection of U2 along V1. Okay, so this is the shadow that U2 makes along V1. Is that making sense? So, what is the shadow? So to find the shadow, you actually can make a picture, complete this picture by drawing a right triangle, which you see here, right? And so if you call theta the angle between V1 and U2, right, in terms of, right, in terms of theta, which trigonometric function can you use to give you the length for the blue, for this side of the triangle? Which trig function would you use? Cosine, right? So cosine of theta should be adjacent. What's the adjacent side? It's the length of the shadow. So that's the length of the projection vector divided by the length of the hypotenuse. Okay? So that means that if you multiply both sides of the equation by the length of U2, you get this. Is that making sense? So far, so good. But there's this formula. If we go back to the beginning of the lecture, let me scroll up. I will copy paste it here. There was this formula for the dot product, right? Which I can, in fact, allows you to solve for the cosine of theta. So it says that the cosine of theta is u dot v divided by normal view or times normal v. So like the cosine of the angle of two vectors is that their dot product divided by their lengths. So if you use that formula here, let me copy paste it. What is cosine of theta? It would be, so what this allows me to do is like, in this equation, I have U2 cosine of theta, but according to this formula, cosine of theta is the dot product of the vectors, which vectors U1, V1 and U2. Divided by the length of V1 times the length of U2, and that equals the projection. Okay. But this is a lot. I mean, it looks like a bit of a mess, but it's not as bad as it seems. Because what is there something you can cancel out, first of all? Yeah, you can cancel this one with this one. And you can also say, what is this value? What's the value of V1, the length of V1? It what is that equal to? The length. It's just one because it's a unit vector, right? That's why we wanted a unit vector to begin with. So what this is telling you is that the projection, the length of the projection is just the dot product of V of U2 with V1. Like, let me write it this way. I didn't mention this before, but it doesn't like the dot product. One of the nice things about a dot product is that uh, it doesn't matter the order in which you write the factors. Their dot product is the same. Okay. So just to go back to the original picture, what I'm saying is that if you had U2 and you had V1 here, the shadow, right? The shadow, which I'm calling the projection, well, it's the length times the direction, but the direction of the shadow is the direction of V1. So it's really U2 V. So the formula for the projection is U2 dot V1 times V1. Okay. Okay, so again, that's the important formula that you need to know. That gives you the formula for the shadow of one vector along the other, which you'll see if you take the multivariable calculus, you'll see again. And why am I doing this? Because if you remember our objective was that I had U2 and V1, and I wanted to use Gram-Schmidt. I mean, the goal of Gram-Schmidt is to do something to U2 so that it looks like this. So the at the step at the end of the process, you get two vectors that look like this, which are perpendicular. So the inside is to realize that this third vector that I had written before, which I used secretly to complete the triangle, right, to draw the right triangle, this is the vector that we're after. If you compare to this picture, right, if you compare this with this, is more or less the vector that we're after. But what is this vector? Well, the vector addition properties essentially tells you that this vector is U2 minus a projection. Okay, but the thing is that that may not have size 1. So for V2, we'll just rescale it so that it has size 1. So let me write it down because it's a little bit tricky. So the formula for V2, here it is that it is this vector that I just drew divided by its length to guarantee that it has size 1. Okay. Is that making sense? We're almost done, I promise. And again, next time I'll give you like the formula more like as a table so that you just have it. But I'm trying to explain like the picture of where it comes from so that at least you have like an idea of what's happening. But again, for the final, as I said, you can write it down on the formula sheet if you want, because it's definitely kind of tricky to memorize. So let's say step 3. Okay, so now the new basis, right? After you fix the second toy, the new basis is V1, V2, and U3, right? So U3 is the only toy that hasn't been fixed at the moment. Okay, and so in step 3, what we want to do is like straighten this one out. So in step 3, what do we have now? We have V1, we have V2. These are perpendicular, so let me draw like a 90-degree angle so that you see it. And then you have U3, which is still maybe not perpendicular to these two. Okay, so there's like maybe an angle which is not 90-degree between U3 and the V1, V2. And so the Gram-Schmidt process, what the last step in Gram-Schmidt will be to turn it into something that looks essentially like a version of the XYZ axis. Okay, that's our goal. This is like the end result of Gram-Schmidt. Should be something that looks like that. Okay, and what's that idea? The idea is like this shadow uh, picture. So if you look at these two vectors, right? These two vectors make up like they make up like a piece of paper. Like once you have two vectors, you can kind of like find a plane that contains them or a piece of paper that contains them. Uh, and so what we want to find, right? I don't know if you can see it here, is that if you put the sun once again, there will be a shadow that U3 makes along these two vectors. So there's like a projection of U3 along the vectors V1 and V2. Is that making sense? Is the picture kind of, let me like zoom, actually make it a little bit bigger so that it's easier for you to visualize. Is that making sense? So you're just looking at the shadow that the third vector makes along the plane that contains these two vectors. Okay. The cool thing is that since these two vectors were perpendicular of length 1, I mean, I guess, well, perpendicularity is a big property. Since these two vectors were perpendicular, to find this shadow, you actually just need to find the shadow along the first vector and the shadow along the second vector and just add them together. So that this shadow that you care about is kind of like a sum of mini shadows. So this projection is actually just going to be like the projection of U3 along V1 plus the projection of U3 along V2. So like the shadows add, that's what I'm trying to say. And they add because we're choosing our vectors to be perpendicular in the previous step. Is that okay? Again, next time I'll write like all these formulas from scratch so that you just have them like summarized. But like the important thing that's happening here is that the shadows add. So let me write that in words. And the vector that we care about, the one that we actually want, oops, is this one. Yeah, in fact, I can, oops, just to make it look better. Let me fix this. The vector that we care about is the red one. That's kind of like this is going to be playing the role of B3, but by the same idea as before, this is actually just corresponds to U3 minus this projection. But again, the problem is that that red vector may not have length 1, so we have to rescale it one more time. And so finally, the last formula here is that this is U3 minus the projection of U3 along V1, V2 divided by the length of U3 minus the projection of U3 along V1, V2. Okay. And that's the last one. If you had only 3 vectors in the basis, that's the last vector that you would need. Is that making sense? And the process would continue. If you had a fourth vector, then you look at the shadow of that fourth vector on the space on the cube that contains these 3. The problem is that that requires a fourth dimension, so you cannot really visualize it as easily, but it will be the same idea. Okay, so but at least I wanted to explain to you today, like the concept behind how do you come up with the formulas. So next time what I'll do is just write you like the general formula that works regardless of the number of vectors, and then I'll do an example. But as I said, like for like this, like you'll see, these examples are kind of long. So for practical purposes, like I would just probably give you at most like 3 vectors for you to do Gram-Schmidt over. So you'll see next time how it works. It's just like you just have to do a lot of dot products basically. Okay, but yeah, if that sounds good, that's what I wanted to tell you about today. Unless there are any other questions, you're free to go. I'll upload the video YouTube and also send you the PDF file of the notes that I wrote. Thank you. Have a good day, you too. Bye. Yeah.